Hello and welcome to this course. I'm Dr. Sriram Kumar. In last class, I discussed our nanomaterial synthesis using chemical methods. In chemical methods, we understand the key important parameter that is nucleation process and the growth process. What is the difference between homogeneous nucleation and heterogeneous nucleation process? And then after we understand the key steps in the nucleation process, maybe so for the growth of the nanomaterials, we should have a critical size for nucleation process, and then after there is the further growth of nanomaterials formations. And we also understand the three different cases in which we have. One is the kind of the very fast nucleation process and growth process. Second, third is the ostward ripening process. And we understand the difference between these three processes and the effect of this process on the nanomaterial synthesis and the size. And then after we understand the key aspects of the nucleation process using thermodynamics straight, we understand how nucleation happens from the liquid phase of the system. And based on that, change in the Gibbs free energy and the surface energy, we calculated what is the critical size. We calculated here the critical size of that embryos, and that is the nucleus, and that depends on here surface energy and delta G V, and that is for the Gibbs free energy per unit volume. And we have calculated this one, and based on that, we also calculated what is the change in Gibbs free energy for that critical conditions, and that is the measurement of the energy barrier for nucleation process from liquid into the solid form. So based on this one, we will further understand what are the effects of temperature on the nucleation and the growth of nanomaterials. So if you want to understand effect of temperature, so here we have here the surface energy. So here is the delta GV, and delta GV that depends on here the KT. That is and we have the temperature here. So and here and because of this temperature, so that energy. So here we get that energy difference here, right? So we have this energy, and that is the function of temperature. So based on that, this temperature, we can explain, okay, if we have the higher temperature, in that case, we have the smaller barrier. So this is the case. So this is the T1 temperature. So for the T1 temperature, we have that is the critical size of the embryos, maybe the nucleus. And for this one, we have this delta Z1 star. And when we increase temperature from T1, so here T1 is less than T2 and less than T3. So if we increase temperature T1 to T2, what happens? Because here this value will increase, what happens? This value will decrease, right? So what happens? There is a decrease in the delta Z2 star, and at the same time, so that will also get changed because here R star is equal to -2 by delta GV. So if these values will increase at higher temperature, what happens? There is decrease in that radius, and that's why there is the shifting from higher particle size to the lower particle size, and then further decrease to the helium. So if you increase temperature, what happens? There is a decrease in the size of nuclei. And based on that size of the nuclei, we can control the size of nanoparticle. And that is a very important finding. If you want to control the particle size, maybe if you want to make a smaller particle, if you want to make bigger particles, so based on that, you can control that temperature of reaction, and that reaction we can understand the rate of nucleation process and the growth process, right? So here in the if you so here the Tm is the melting temperature. So here that is melting temperature of the solid, because we are making solid into the liquid into the solid phase. So here this melting point Tm is the this melting point of the solid material. So what happens here is, so here if you have very low temperature, so if you increase temperature from this particular temperature, what happens if you are increasing temperature in this particular exit? Uh, Reaction there is slowly in, so there is the kind of the increase in the nucleation process, and after at particular temperature here, and this particular temperature you have maximum nucleation rate, and then after that particular temperature there is again decrease in the nucleation process, and that is the again there is the lowest in temperature towards the melting temperature. So we need to understand, so using this kind of those signatures of the nucleation rate at a different temperature, we can increase or decrease the nucleation rate, and that nucleation rate we can control the particle size. And if we just, so this is the nucleation process, and the growth rate increases with the temperature. So from here, if you increase temperature, what happens there is kind of the exponentially increase in the growth rate of the nanomaterial. So from the solid to the liquid, if we have increased the nucleation, so if you have the very nucleations or nuclei, we have the different nuclei here, what happens? So with the increase of temperature, you have this particle there, right? You have the particle there in the solution. So you use something in solution. So with the increase of temperature, what happens? There is the diffusion. So yeah, so there is the diffusion process happening, because of the higher diffusion of that desired M plus to the surface. What happens? There is increase in the growth rate. So based on that, we can, so here, so this one is the nucleation process, and this is a growth process, and based on the increase in temperature, we can increase the growth rate of the nanomaterials synthesis process. And if this combine the growth phase and the nucleation process, then we will have the overall transformation rate. And this transformation rate has the maximum rate at that particular temperature. So whenever you want to design your experimental setup, we need to consider these two parameters, nucleation steps process and the growth process. And based on these two parameters, we need to find out overall transformation rate. And then based on this transformation rate, we can put and use that optimum temperature. So from here, we understand effect of temperature on the rate of nucleation and the growth process. And in the previous slide, we understand the effect of temperature on size of nuclei or the nucleus and the energy barrier. So whenever we increase temperature, there is a decrease in the energy barrier. At the same time, there is a decrease in the nuclei size of the nucleus or nuclei. So if you decrease the size of nuclei, so if you have the smaller particle size, and if you have higher temperature, then it will also increase in nucleation rate and the growth rate. So we have the smallest particle size. So we can explain these observations based on these two and the plot. And further, if you want to understand effect of kind of the concentration, maybe the viscosity and energy barrier, we need to understand this kind of the mathematical relation here. So in the thermodynamics, if you want to know what is this probability of those converting reactant into the product, so we can explain with respect to this energy barrier. So if you want to know what is energy difference here, so this is for liquid and this is for solid. And if we are making solid from the liquid state, so from liquid and solid, we have that energy barrier, right? And that is the activation energy. and from the solid to liquid, and there is the increase in the activation barrier. And here delta Z star is kind of the energy barrier between the surface energy and the volume energy. And if we have those initial concentration, we have the number of the growth species per unit volume, that is the concentration. Then we can know what is the rate of the nucleation process happens, and that depends on the initial concentration C0, it depends on temperature, and that depends on viscosity here. So in this case, if we have higher initial concentration, we have C0. If we higher initial concentration, there is increase in the rate of nucleation process. If we have the higher temperature, that means that we are increasing nucleation process. And if we have lower viscosity, so here if we have the viscosity here are in 1 by in eta. So if we have the lower viscosity, that means we have the higher faster rate of nucleation process. And we have the other parameter, that is the barrier, and this barrier is about delta G star, right? So the rate of nucleation process depends on the initial concentration, viscosity, and the delta Z star. So this is one kind of the set of those parameters. And second is that if we just increase the number of the nuclei of at the same concentration, if we have the C0, but if we just increase the nuclei of the smallest size, in that case we have the smaller nuclei, and that will lead to the smallest particle size. So this is really important observation for the controlling of the nucleation process. So if you want to understand the difference between homogeneous and heterogeneous nucleation process, so what happens is, if you just understand this figure, so we have delta Z there, so there's a volume contribution and a surface energy contribution. So here we have the energy barrier. So this energy barrier is for the homogeneous nucleation, and this barrier is for the heterogeneous nucleation. So based on this plot, so heterogeneous nucleation has less energy barrier as compared to the homogeneous nucleation. And this was the same explained in this particular uh, that there is the in the homogeneous nucleation we have the higher energy barrier, that is shown in this particular figure, and in the heterogeneous nucleation we have lower energy barrier, right? So using this observation we understand that okay, there is a small energy barrier for the heterogeneous nucleation, however higher energy barrier for homogeneous nucleation, and that will affect the rate of nucleation process. So we need to understand here why there is a difference in the energy for homogeneous and heterogeneous nucleation process. So we can explain that this difference in the energy between the homogeneous and heterogeneous nucleation using kind of the surface energy here. Suppose we have here, so this is the external surface. So this is the foreign particle surface there. And if you want to understand here, this surface, so we have the solid surface, and that solid surface we have this job there, right? So based on that job, we need to know what is the surface tension there. So if you just consider the heterogeneous surface, in this case, we have, so here this surface energy, and the surface energy between drops and liquid, and this is the surface energy between liquid and solid, and this surface energy, surface tension is between solid and drops. So this is the three different kinds of the surface energy, and here the theta between this one is a theta angle. So if you want to calculate overall uh, surface energy, so we can write here dl cos theta. So if you just write in, so this one on this axis, so we have this cos theta plus we have this gamma uh, is D is equal to SL. And if you just write, this is drop in liquid cos theta is equal to SL minus SD. So this is the energy difference. So that is the new surface energy. And if you just put this value in the previous value here in previous value, we have overall energy is the one is the volume contribution. So that volume contribution was 4 by 3 pi r cube. We have delta V, and we have 4 pi r square, and that is the energy difference, and that is the gamma dl. Right. So that was the previous surface energy. Now we have this surface energy. So we need to modify. So this is for homogeneous process, and for heterogeneous process, we need to write here delta G R is equal to 4 by 3 pi r cube delta GV plus 4 pi r square on D. So this is dl minus this one is the pi r square dl cos theta. So what happens is this values is less from this initial surface energy, and because of that we will have the different delta G value. If we just find out the different R, we have the different delta values, and we will have the different critical size, and based on that critical size we will get the different R delta G values, and based on that we will have different energy. So here it is the we have the smaller, so we have this kind of this is, so what happens kind of things here, where we will have these values is smaller than the previous critical size, the embryos. So based on these observation and derivation, we will understand why heterogeneous nucleation process has less energy, less barrier as compared to the homogeneous nucleation. So we just understand this is the energy barrier. Energy barrier for nucleation process. Nucleation process. So this is all about the difference between the homogeneous and heterogeneous nucleation process. And if you want to understand what is rate, nucleation rate for homogeneous and heterogeneous nucleation, so let's understand, since heterogeneous nucleation has low energy barriers, so in this case we have the higher, so in this case we have larger, higher nucleation rate as compared to the homogeneous nucleation, right? So based on that we can explain which kind of the mechanism has the higher nucleation rate or the smaller nucleation rate. Okay, now further we need to understand the other key point, and that other key point is about, so if you want to grow the nanomaterials onto any surface, so we have the four key parameters. One is the generation of the growth species. Second is the diffusion of the growth species to the surface, adsorption process, and the reaction on the surface. So so based on these four steps in the growth of the nanomaterials, we have two kind of mechanism. One is diffusion control growth, and the second is surface process control growth. So here, if you want to understand surface growth, so if we have this is solid material there, and you have this one. So what happens? That needs to diffuse towards the surface if you want to grow that nanomaterial on the surface. So here, this metal ion should diffuse from the bulk to the interface. So we need to understand. So here we need to know what is the Mn plus. So this is kind of the adsorbed, adsorbed Mn plus. So that this concentration is different from the bulk concentration. And once we have the adsorbed, so there is kind of the process happens, and there is the formation of the metal or atom there. And then there is formation of embryos, nuclei, and the nanomaterial. So what happens if this process, so if this process is slow process, if this process from the bulk to the surface is a slow process, so this mechanism, is called diffusion control process. And the second kind of the process is about the surface process control. So here, if this is slower process, if this process is slow process, in that case, this process is called surface process control process. In this case, this process is faster and this is the slower process. So we have two kind of process. So now just understand each process one by one. So let's first consider diffusion control process. So in diffusion control process, we have, so what happens here is this condition is written here if C is, so C is bulk concentration, and here that is the C minimum concentration which is required for the nucleation process. So if the bulk concentration, so this concentration is less than C minimum concentration for the nucleation process, what happens? So there is no further nucleation process, and there is only the kind of the growth process happen. So we can explain this observation using this kind of graph. So we have time and we have concentration. So we understand that we have two kind of things here. Sorry. Let me write. So what happens? We understand that here, this region is the nuclear. So this is nucleation. So this is nucleation process, and this entire region is the growth process. So here, so in this particular case, so for this one, we need absolute concentration of this one. But here the concentration is less than this critical concentration. Here in this particular zone, we have the C is less than C minimum, right? So in this particular condition, there is only growth process happens, not nucleation process, right? So we have only the growth process. So if you want to understand what is the growth process and the control growth rate, so we can have using this the fixed law of the diffusion process. So using that fixed law of diffusion process, we can understand. So we have from the fixed law. So we have this fixed law is that we have R by dt, and if this minus C d C minus CS Vm by R. So in this particular equation, this is the growth rate of the nanomaterial, and here this is the diffusion from the bulk to the interface. C is the bulk concentration, and Cs is kind of the surface concentration, and V is the molar volume, and this is the size. And if you want to understand the critical values here, so we have R dr is equal to d C minus Cs Vm dt. And if you want to understand the radius, so we can integrate from 0 to t. So initially we have R0 and we have R here. So if you just solve this one, we have r square by 2, r 0 is equal to d c minus cs vm, and sorry, we will have t, right? And if you want to further write this one, minus uh, 0 square is equal to 2d c minus cs vm t. So from this relation, we will have, so from this relation, if you just write here r square is equal to 2d c minus cs vmt plus r0 square. So we can write here equal to kd t plus r0 square. So this is about the size of the nuclei in the diffusion control process. And if you want to understand what is the difference in the size of the particles, so if you want to understand the difference in the size, we need to understand what is the change in R values. So this is change in R values we can calculate using R0, del R0 by R. So if we have here del R0 divided by, if we put this value here, what happens? We have k d t plus r square to the power 1 by 2, right? So from this one, we understand that change in the size of the particle indirectly proportional to 1 by to the power 1 by 2. So if you have the diffusion control process, that means that takes very long time from bulk to the interface. So in this case, if you have the larger time, what happens? You have the change in the size of the particle is very small. So what happens here is initially you have the bigger size or the different size, but after some time, what happens here? You have here that diffusion control growth promotes the formation of the uniformly sized particle, because what happens here is at longest time period, what happened? We have tail, so we have very small difference in the delta R values, and based on that delta R value, we have the uniform. So that means we have uniform particle size. So this is the important things while in the growth process happens. So this is about the diffusion control process, where in which we have that is the limiting step. And the second process is about the surface process control growth of the nanoparticles. So in this case, we have the rapid diffusion of that particle from the bulk to the surface, but there is the surface process is the slower process. In this case, we have the concentration on the surface is equal to the concentration in the bulk. So these are the understanding about the surface process. So in this case, we have those two kinds of mechanism. One is mononuclear process, and second is the polynuclear process. So now let's understand one by one what is the mononuclear growth, and second is the polynuclear growth on the nanoparticle. So in mononuclear growth, so that process happens layer by layer formation of nanomaterial. So what happens? There is one layer formation, and then after there is a layer by layer formation in the mononuclear growth mechanism. So in this case, what happens? There is enough time for the growth species to diffuse on the surface. So we have here surface, and we have this one, and here it comes on the surface, and then there is the formation of the atom. So what happens here is this process is a fast process, but this process is slow on the surface. So that means that has the enough time to come from the bulk to the surface. And in this case, we have that growth rate that depends on the surface area. And we have the here, the rate for the that growth process, we can have this way dt is equal to km c r squared here. And if you just solve this one, dr by r is equal to km c dt from r0 to r and 0 to t, we will have 1 by r is equal to 1 by r0 minus km t. And based on this size, we if you want to know what is the change in the size of the particles from this one, we have del 0 upon 1 minus km 0 t to the power 2. So in this case, so these values is very, very less than 1. So in this case, where we have del r is equal to del r. So in this case, what happens? The change in, or maybe size, the change in the particle size is similar to the size at initial stage. So so in this particular case, there is no such kind of the monodispersity of nanoparticle. And in the second case, we have the polynuclear growth stage. Here we have the occlusion surface is very high. And in this case, we have the growth rate is that dr by dt is equal to kp. And if you just solve this one, dr is equal to kp and dt. And if you just solve 0 to t, r to r, we will have r is equal to kpt plus r not 0. And so this is the radius of the nuclei. And if you want to know what is the change in size, so we have the similar size at the initial stage. So again, there is no such kind of a dispersive change. So in this case, we get the bigger particle, and there's no such kind of the uniformity of this particle. So from this kind of the discussion and concept, we understand that the diffusion control process is a desired process, because in the diffusion control process, we have uniform particle size of the materials. So here we in the diffusion control process use low concentration reactant, that is increase diffusion distance, and because of this distance, we have increase in this time, right? And the second is the increased viscosity of the solvent. So because we understand the rate that is about 1 by eta. So here what happens, we need to use the low concentration of reactant, right? So what happens in the diffusion control process, we need to play with the concentration. So we need to use the low concentration. At the same time, we need to use in higher viscosity of the solvent. The second is the diffusion barrier polymer on surface. So if you use kind of this polymer, or maybe what happens? So there is an increase in the, so there is slowdown process happens. So these are things, and this controls apply to growth species, continuous injection, or maybe in situ preparation of the reactant. So these are the things we need to consider if you want to synthesize nanomaterial. And we can play with the concentration, we can play with viscosity and the diffusion barrier. So if you want to understand the change in the particle size, if you want to understand the change in the particle size with this time, so here that control growth at the diffusion process. So initially there are sometimes there is an uniform distribution of the particle size. And however, if you have the surface process happens, so there you have the larger difference there. So this is all about nanomaterial synthesis. So in this particular class, we understand the factors that can affect the nucleation process and growth process. And further, we understand the difference between homogeneous nucleation and heterogeneous nucleations. And in the real time, if you want to synthesize a nuclease for the practical purpose, we should go for the diffusion control process because that has capabilities to make uniform particle size. So this is all about nucleation and the growth of nanomaterials. In next class, we are going to learn colloidal nanomaterials